Hey everyone, and welcome to your research statistics and literature critique lecture. And the main goal of this, aside from giving you some more tools and understanding in how to approach research and research studies and how to evaluate them on some level, but also understand them for potentially your own research purposes, is to help set you up for the exam and our research project. So, let's dive into things. To kind of frame roughly what we're doing in class, but also the scientific method in general and a kind of general process. And you might see a number of variations of this out there, but more or less we start by asking some sort of a question about the world around us that might be interesting to us or seem like to have an obvious pattern. And the great thing about science is we just don't observe and make opinions. Is we observe and we test and we see if there is some more power or truth behind that initial observation. And so part of that process is to do some background research, and then you make your hypothesis, which is your actual thing that you will be testing, and we'll talk a little bit about that and the format that should look for yourselves in today's class in particular, or in this course. Then you actually test it. So that whole process, those four, even though you might not have asked the original question, you'll be given prompts to do the background research and gain a deeper understanding on top of the course material we've already done on some of these topics. Create your question or your hypothesis you're going to test and do the test. That's all leading up to your first presentation. So day one, where you do your data collection, all of this kind of occurs in the background. And then as you move forward, you get your data back after you conduct your experiment on your classmates. And at that point in time, it'll be up to you to analyze, look at the data you get, understand it based off of largely today's lecture, and then decide if the hypothesis is true or not true or somewhat supported or not. And then you're going to report those results to the class in your second presentation, which will primarily be this part. And knowledge transfer, just to speak to that too for a moment, is one of the more important parts of science, and it's also part of the scientific world and academic world that I feel is done often relatively poorly. If we think back over the last 5 years or so, this being 2024, there's been a lot of disparity between the general public and general population and science and the academic world. There's kind of been this divide that's been put there due to various factors. But I think it's up to science and those in academia to be able to present and transfer the information and the knowledge they gain through research to the general population. That's the end goal, because if we don't provide this information to everyone, what is the point of generating it, right? Okay. So this is the goal for this second presentation for you, is do your research, gain some knowledge, and then pass it on to your classmates to essentially help them prep for the final, but also understand the course material a bit better. Okay, so first of all, what we're going to look at is essentially how to find peer-reviewed articles. I know we've already done a library session, which part of the focus was on sourcing peer-reviewed literature. But I'll add a few more tips in there because, again, the goal is for you to find many different articles on a specific topic. So a few of those approaches come from, well, the first one is changing the keywords that you use in your search terms. Now, you might have noticed when you're doing your library database searching that there was a very specific kind of process you needed to do and come up with very specific keywords. And oftentimes, if you're feeling like you're getting stuck and you're not finding exactly what you are looking for, oftentimes expanding or changing your key keyword search terms can really help. And it's a little tricky sometimes. It's nice if you have a group to help you out with this. But if you're an individual and just trying to come up with synonyms for, exercise science or kinesiology or exercise physiology, or, you can kind of run into a bit of a barrier after a certain point of time. But again, being able to do that is really, really helpful and kind of give you a lot of different search results depending on what area of study you're trying to find. So that's the first one. And one of the best methods to do this, and it's often brought up in evidence-based practice. So when you're a clinician and trying to find some information to help a particular patient or client out, and that process is called a PICO search. So that stands down here, PICO. So PICO search it's an acronym. It stands for population or patient, depending on what you're looking at. I stands for intervention. C is comparison. So a comparison group or a control group. And the last but not least is outcome. So what was the outcome measure used? So to kind of go through that again. So your patient or population would be people with diabetes or a diabetic, type 2 diabetic population. The intervention might be aerobic exercise. Okay. The comparison group, usually if there's a control or comparison group, typically you're comparing to like a placebo in certain interventions, like in rehabilitation or exercise physiology. Sometimes that's just education about a certain disease state, and sometimes it's nothing. So occasionally you can leave out the C when you're doing your searches. And then O is the outcome. So outcome for diabetics who exercise lightly compared to just using insulin. Maybe the outcome measure will be blood sugar levels being less variable. Okay, and so when you search these things, you're trying to find something very specific for that population, the intervention type, and then what the outcome measure is. And those three things together, if you change a key search term for any one of those things, will definitely oftentimes give you more search options or more results. Okay. So that's the first one. The second tip is going to be researching authors. So if you find a particular study that seems really, really great, it's right in line with your content that you're trying to find. If you look at the main authors of that research, and it's usually the first author that's listed or the first researcher that's listed in a peer-reviewed study, typically they'll have a whole bunch of research in that area. And so you can simply, again, change your keywords in your searches and look for, Dr. Smith and all the research that they happen to do in a certain particular field. So that would be, again, your author searches that you change. And the last but not least would be changing your database. So again, going from something like EBSCOhost or a database that the school provides for you, and then also looking on Google Scholar, even with the same key terms, can potentially give you more or new or differing articles that are in line with what you're looking for. Okay. Good. So once you have that, and you have found your study, where do you actually find the content and the information you're looking for? Again, oftentimes, nowadays everyone's feels pressed for time, and so being able to do things efficiently is great. Once you have your peer-reviewed study and you're trying to source some particular information quickly and easily so that you know if maybe you can use a certain intervention with your patient, or maybe for the purposes of this class, you're trying to figure out whether the research article has any relevance to your experiment, again, it's good to know where to look. So we start off on a research paper at the abstract, and that gives you a summary of the entire study. I find a lot of variability in abstracts, and APA So the kind of organization that dictates the format of academic papers that is often followed. I find the format, kind of varies between study to study. So you may or may not find quickly and easily right on the first page in that summary the information you're looking for. But oftentimes some authors will hide some of the good information so that you actually have to purchase the study. I feel that's done less nowadays, thankfully, to kind of increase the flow of information. The next section that you'll find is the introduction. The introduction or literature review, which hopefully or typically is done in that section, is really great to find where the previous knowledge base for this particular topic has gotten to. So if you're even just trying to further your own knowledge in a certain area, a lot of the times the introduction is a really great place to review and see where things are. It's also a good place to find authors that are really prominent in a certain area of study. And then again, you can search for those authors, and typically, they have a very highly cited paper, which means it's very foundational for a lot of research, and is a good place to look for general background information. Okay. When you're doing your presentations, in particular your second presentation, a lot of you will be sharing your own research articles that you've each sourced in this particular section, because again, it gives the whole class, a bit more background information and knowledge about what your particular area of study is looking at. The next part that is presented is the methods. So methods is it's like a recipe. So if you were to create a method section and give it to another scientist or academic or researcher and not say a single word, they should be able to totally reproduce step for step how you went about conducting your own experiment. And even if you're not a researcher or planning on conducting an experiment, it's for you, the reader, to be able to, in your mind, know exactly, again, step for step, what the procedure was that these researchers followed. Again, some authors do this better than others. And I feel this is one of the more important sections for science as far as being able to peer review and critique and understand a certain group of researchers or researchers' methodology and therefore their results, right? This is kind of the first place where, if there's holes in methodology or shortcomings or limitations, it will obviously show up in the results and conclusions that these researchers do. So if you're trying to find things out about the population that they studied, the study design, measurement tools, so outcome measures, all of that will be in the methods. A good results section will be purely just the stats without making any conclusions. I feel oftentimes some students might feel the results also explain why the results happened. That is saved for the discussion. So results are purely the maths, the statistics ran, why they were ran, how they were ran, that sort of thing. But are not making any conclusions. It's just a statement about the numbers and statement about statistical significance. Okay. What you're looking for, if you're looking for an explanation as to why the study found what it did, that's in the discussion/conclusion. So at the end of the paper, that's where we're looking for interpretation of the results that were found. And any they may or may not list some current limitations for their study. They'll definitely highlight the strengths and kind of explain their results. Okay, and so that will be in the discussion section. Okay, so now we'll get on to constructing a hypothesis. And really here, your goal is to make a statement, okay? Because what you're ultimately trying to do is stay through this test that we're going to do, this study, is there support to say that this is true, or is there not any support there? And that's how you make a testable hypothesis, okay? You're not posing a question, you're not mulling about observations, because those things are harder to find a yes, there's support, or no, right? There are exploratory studies and stuff like that, but for the purpose of this course and what you'll be doing with your experiment, you want to make a very clear statement, okay? And more or less what you're trying to do is make a prediction of what the outcome will be, right? It's not like what happens if people drink caffeine and then take a reaction test, right? Or a reaction time test. You want to say, okay, when people have caffeine, their scores improve by becoming quicker on a reaction time test. So now you can say, yes, there was support for that, or no, there wasn't. If you're saying, what are the effects, and posing that as a question, your outcome measure may or may not actually measure anything that was an effect of having caffeine before taking this test, right? And so oftentimes when you're making a statement, there'll be an if-then statement. So if people have caffeine before doing a reaction time test, then their times will be reduced, or then they will become faster at their reaction time tests. Okay, so if then. Okay. Yeah. And so one of the things while you're developing this hypothesis, and when you're doing critiques or analysis of other peer-reviewed papers, is to look at the hypothesis variables, or just the variables of the study. In particular, the independent variables and the dependent variables. So your independent variable is anything that the researchers have manipulated or changed to see if there was a difference. So this would be like your intervention and your control, right? So that variable, whatever happens to be changed between the two, is your independent variable, right? So if I'm trying to compare, I was about to use an example from the next slide. Maybe I wanted to compare the difference between, let's say, strength training and endurance aerobic training on cognition or cognitive test taking. Okay, so my if-then would be like, if people strength train, then they would perform better on a cognitive test. Okay, so is there or is there not support for that? And so my independent variable will be the type of exercise, or exercise type, right? And so it would be strength training versus aerobic training. Okay, so that's what's controlled and changed. What my outcome measure on that specific example would be the cognitive test, and the, let's say it was an IQ test. So what is the IQ score? That's my outcome measure. Okay, it's not the amount of weight on the weights I was lifting, or the time or intensity of the endurance program. It's what I'm actually trying to see as the result of, or affected by, my independent variables. Okay. I think a key point here to make when you're critiquing information, but also when you're trying to develop your own experiments, is looking to see what the operational definition of each of these variables are. And I think that's something that a lot of stats and research classes mention, but maybe don't highlight quite enough at times, is how you define your variables can greatly affect your outcome. And it's often an overlooked place to critique a paper. So here's an example on what operational definition is. Essentially, you have a variable and you define it by whatever your study happens to define it by. So for example, if to go back to the strength training program, if I define a strength training program as lifting, resistance training, full body, two times a week, or 2 to 3 times a week, and consistent for 2 months, right? So if I have a population of people that do that and meet those requirements, then I'm like, okay, based off this study, I'm defining that as an appropriate strength training population, great. If people don't meet that threshold, so say they only strength train once a week or once every other week, then they're excluded from that definition. And the reason I want to highlight that is a lot of results can get very skewed in different directions based off of that definition, right? So what if any strength training has an effect on the dependent variable? Well, by not excluding people that just strength train once a week, we make our results maybe a lot more augmented or greater, because we're only taking people that strength train 2 to 3 times a week. But the effect could be a little bit smaller if we had included people that strength train once a week, right? So again, how we define these variables is really important to the results of the study, for sure. Okay. The other part of it is determining validity. And so a good example of this would be if we're to look at, let's say, aerobic training programs. And one study wants to include, let's say, anyone who walks, jogs, or does CrossFit or high intensity training. Okay, and then they measure stuff like, let's say, VO2 or aerobic capacity, measures of aerobic capacity. And in the one sense, we've included a bunch of people that do aerobic activity, but also HIIT training, which is kind of this cross between some strength and aerobic. It's really anaerobic activity. So is that really looking at individuals that have aerobic capacity or might build aerobic capacity? Well, maybe not. And so when you're getting your results as far as the outcome measure, is that really a valid process? Are you actually measuring what you're hoping to measure by including these people in this group? Another way of looking at that would be if you had a bunch of people that did resistance training and strength training, and then you did a aerobic test on their fitness capacity. So when you're looking for the results of a strength training program and you measure something that is measuring aerobic capacity, there's an incongruence there, and therefore it's not a valid test to measure what you're hoping to capture. And so typically this will get caught in the peer review process, but occasionally you'll find things that are testing kind of adjacent concepts to what's actually being tested. And there's logistical reasons and stuff behind that, but I think it's an important thing to look for when you're trying to use research and apply it clinically, or if you're doing like a research kind of critique for a class or something. Okay. I think we already spoke about hypothesis testing, just kind of the last point here. So essentially you're trying to formulate a prediction, and that prediction is modifying the independent variable, and what you're trying to find is what changes on your dependent variable. Okay. Great. So I have 3 scenarios here. I highly suggest you kind of like pause the video here, give one of these, try to wave you down if you've gone on to other activities, so I have just been listening passively. So pause here, take a read through each one of these scenarios, and in each of them try to identify the independent variable and the dependent variable. Okay, I'll give you kind of a moment to do that. Okay, hopefully you did that. We'll chat about it just here in brief, as I think once you see it, you'll be like, yes, I kind of get this. I'll flip back and forth between the two. So in scenario 1, we're looking at different types of exercise on weight loss, so aerobic versus strength training, and those are independent variables because that is what we're manipulating. That's what the researchers are changing. Our dependent variable is how much weight was lost. So you could say either kilograms or pounds or whatever unit of measure was there. Okay. In our second scenario, that was to do with university athletes and how sleep might affect their cognition. how sleep affects their performance. So sure enough, we have our hours of sleep, and it's operationally defined into 3 categories of less, appropriate, and too much sleep. Too much. And athletic performance here is measured through specific tests, such as sprint time, jump height, and endurance capacity. Again, that would be dependent on the type of sport or athletics that you're trying to measure. If you're measuring a whole bunch of different types of sports that require a whole bunch of different physiological components, it makes sense to measure them all, just to ensure that you have validity, right? Scenario 3, hydration level and cognitive function. Again, we're looking at hydration level here, fully hydrated versus dehydrated, and then a bunch of different cognitive tests. A note about hydration is I did a study like this in my undergrad, and what's kind of interesting is it's really easy to actually measure. It's essentially the amount of weight loss that occurs through the duration of time of a particular activity minus whatever weight of water that you drank during that time, right? So my study was on beginner Bikram students and how well they were heat tolerated, or if they hit a clinical status of dehydration. And what I found was most people, both whether they were just beginning or whether they had been practicing for a while, but mainly the beginners, almost every time at a very high frequency hit a dehydrated status. So what that is a drop of about 2% of body weight from before to after their session of Bikram or hot yoga, right? So yes, that was interesting. And again, just 2% of your body weight is a sign of dehydration for sure, if that's purely through water loss, which was a safe assumption to make with the 90 minutes of hot yoga, for sure. Okay, great. So once we have designed our experiment, we can run it, and then, of course, we get our results. So what do we do with our results? Well, there's a lot of statistics and some math stuff that we'll typically need to know or do. In this course, we don't actually have to perform those functions. That will be done for you by the lab facilitator and then returned to you. But what you need to know is how to read them, interpret them, and when you're looking at a peer-reviewed study, you need to understand what was going on and what those terms mean. What does it mean when you're seeing a value for central tendency? What sort of effects does that actually have? Because the authors sometimes, maybe, if you interpret it this way, might be overselling the results of their study. You know, they might be like, oh, we had statistical significance and we had this great effect, which we can say with like a lot more certainty that our independent variable affected our dependent variable in this meaningful way. Here's why, but if you go back and look at the results, you're like, ooh, that was pretty close to not being statistically significant. Therefore, are the conclusions you're making valid, right? So I digress. Let's take a look here at results and stats and how to interpret it. So one of the first things that we can look in our results section is we're looking for things such as central tendency. So where do most of the results or scores go to? And then how much variability is there? So from that central grouping of results, how variable were the results? Is it very random or not so random is another way to say that. Okay. And then in this section, you'll see it displayed in a bunch of different ways. I think I want to make a couple of notes about pictures and graphs and stuff like that, because that is definitely something you should strongly consider to include in your second presentation when you're presenting your results. But I think the importance to pause and clearly explain what your table or graph or chart or whatever is showing is really, really key. Okay, so understanding what it shows and explaining that is important, right? And so to do that, you'll need some of this information. Okay, So when we're looking at central tendency, we have a few different terms or ways that we can look at that. We have our mean, which is the average. So you add up all the numbers, divide by how many numbers you have. That gives you your average. And that gives, again, an idea of central tendency. We have our mode, which is just the most frequent number, and median. And median and mode, depending on what you're looking at, can provide some extra insight into your results. And but typically they aren't too often used in research, broadly speaking. Okay, they kind of show a it might be a little less valuable in the information it gives us. For example, when we're talking about a middle value, we're literally talking, let's say you have five scores that you collected, or 5 bits of information. You go from either end and you work your way to the middle. So the third number, or the middle number, is just the median number, which, maybe they're all really, the first 3 scores are really, really high and the last 2 are very, very low. Is that an actual true representation of our central tendency if it's just the middle value? I don't know, I think that's a little less helpful for sure on that one. And then we can talk about that variability, right? Away from that central tendency, or let's just kind of say average for now. And there's 2 things we can look there. We can look the range, so the highest and lowest value. That gives us some indication of, the extreme values that are variable kind of scores reached as far as our results. And then we can also look at our standard deviation, which gives a bit of an average of how far the scores were from that central tendency, or from that central means. We're going to get into standard deviation a little bit more here in a moment. Same with range. So if we actually want to calculate these things, we look at our range, highest and lowest, and subtract, and then we get our range there. So a range of 4. In this particular case, if we have a mean of 5, and our range goes from, let's say, 1 to 6, or 2 to 6, our range would be 4, right? Our standard deviation, though, that's a little bit, I would say, more commonly used and a bit better in explaining our general variability from the central mean, or you don't need to know how to calculate it, but just to understand it and conceptually be able to understand what it's kind of indicating. So how do we interpret that? So if something has a low standard deviation, you're really saying like how far out the data points are. So if it's low, it's all really close to like kind of the middle, kind of average central number, or the mean. If it's a high standard deviation, that means the scores are really spread out. And I'll show a couple of examples of that, but we'll kind of look at this to kind of step back a little bit. Typically when we're looking at something to do with standard deviation or statistical kind of analysis and looking ultimately for significance in that realm, we often find that a lot of our data and information from these studies can be plotted onto something like this, which is a normal distribution, or a bell curve. And what that means is we have a very small percentage of scores farther out farther out in variability from the central mean on one end, and a very small percent on the other side. And most, as you can see, about 68% of our score falls here, right at kind of where the mean is, right? So one standard deviation, or one, let's say, variability unit from the mean outward, we have over half. So a majority of our results fall within that score. And so these scores, again, depending on what we're measuring, can vary, right? So to give some real numbers, just to try to help understand that a bit more, if we have our mean of 50, so we can say this number here, the score at 0 deviations, is 50, right? Kind of along this line. our standard deviation is 10. So going plus 10 would give us 60, and going minus 10 would give us 40. So again, between the scores of 40, 40, and 60, we're going to have 68% of our participants or results or scores within that realm. Okay. Again, going out one more, 30 to 70. Well, now we have nearly all the scores minus, let's see, about 2, 4, 5% of people. Okay. So that's standard deviation, how that kind of works with our scores. It's like a plus or minus range where we can find the majority of our scores. All right. Here's just a slightly different way to kind of illustrate that. So if we have the same mean number of 50 here and our standard deviation is smaller or low, as I said, we're going to have a lot of our scores very close to that mean. If we have a higher standard deviation of 10, we'll notice that more of our scores are kind of spread out, right? And so if we're looking for an effect on our dependent variable and we're noticing that there's a very small standard deviation, what we're saying is there's very little variability, which means that there is more likely to be a higher effect from our independent variable on our dependent variable, that quite a few of our respondents or our subjects or participants in the study had, and that tended to be less variable. So there was less chance that you had more extreme scores away from that central tendency, okay, or that central mean. Okay. All right, so what can we do from here? Okay, so we have this understanding now. We have these central tendency scores. We have these variability scores, or ways that we can kind of look at variability. Well, how do we get these? What do we do with the numbers to get here? Well, we run some statistical tests, okay? And typically we have a couple of choices to figure out how to go about that. One is a t-test. So we kind of have two different groups set up for comparison, and we try to figure out how different they are. Okay, so if their score is really far apart, we know there is a big difference between those groups. If their scores aren't very far apart, and statistically so, and I'll show you what that means in a moment, because of this chance of error that we set through something called a p-value. It may or may not be different. Okay. The other thing that we can run is something called an ANOVA, or analysis of variance, and really that's just a way of kind of separating out things that are variable due to chance or not. Okay. You'll see ANOVA in a lot of studies because of this point right here, where you have usually like 3 or more different groups or a number of different variables getting compared between a few different groups. T-tests usually just have 2 groups only. Okay, and so again, a lot of studies nowadays, because they're looking at multiple variables, go with an ANOVA analysis of sorts. Okay, so again, these two are primarily looking just for what is the difference between our 2 groups or 3 groups that we have. All right. And so this is an example of a t-test for you. So if we have our kind of central mean here, we have our most common, this is a box plot, most common kind of values between this range. And then we have our full range, so our extreme value that kind of goes up to here. So again, extreme values kind of here and here, but within this box plot, we see where the majority of our values are and the mean. And so again, when the t-test is ran, it kind of goes, okay, well, if this is our variability around our mean, this is like an outlier or like a kind of skewed respondent or participant that is kind of way out here at that line, same here. So they're really just looking kind of at these box plots, and based off the results, is there enough of a difference, or is there a lack of overlap kind of between these boxes? Again, this is using a bit more pictorial explanation rather than statistical. And it can be like, okay, sure enough, like there's enough of this variable that's kind of lies outside of that overlap range. So there is difference between these statistically speaking. Okay. kind of the third way that can give us some insight as to a difference between two variables, not necessarily between two groups, but between two variables, is something called a correlation, or Pearson R correlational stat test. Now, you might notice some hesitancy in me saying that because it doesn't specifically say that there is a complete difference, but it kind of does. Here's what's going on with the correlational test. So we kind of compare these two variables of measures that we have. We have all our participants plotted kind of on the graph. And what we say is we kind of get these scores between -1 and +1. Okay. And the closer to 1, whether it's positive or negative, we're saying the more likely it is to be all on that line. So we're saying it's a very linear relationship. So for example, if our x-axis goes up 1, our y-axis goes up 1. Okay, so there's a very direct relationship between the two. But if it's a score of 0, that's saying there's so many scores all over the place that these two variables don't really share much relationship at all. Well, if it's 0, it's saying there is no relationship. It's all too random, right? And so in that sense, we're kind of saying these variables are very different, right? There's no relationship between them. But it's not comparing two groups of people necessarily. It's comparing two variables. And so that's where it's a little different than, say, a t-test or ANOVA. Okay? But let's go to where the strength and the real value of a Pearson correlational R value is. And that is there a relationship? So how closely related are two variables? So we look at correlation, both the direction of the correlation and that number variable that I said. So for example, if we have a positive, so a plus sign value, we're saying that one factor of the x, again, goes up in y. And so again, we'd see something like is demonstrated in this graph here, okay? What we can also have is a negative factor. And so what would end up happening is we actually have, oh my goodness, that was a terrible line. Okay, let's roll with it. Something like that. So for example, anytime one factor goes up, let's say this goes up 2, we'd actually notice this value goes down 1 or 2, okay? So the x and the y. So that's a negative relationship. Now that can still be a very strong relationship. Again, that could be close to factor 1, right? And that's saying that all, if it's a 0.9 or 0.8, that's saying all our individuals are landing pretty close to that linear line. But it's just the direction or the relationship, as in one factor goes up, the other goes down. So do I want an example? We'll have some examples of this after, but essentially, yeah. Also, I'll wait on that one. So we got a little practice test coming up on this. So you'll be able to see an example of that. Okay, and again, this ranges from -1 to +1. Okay, so all this does is give a correlational relationship. It's not causal. It's not cause and effect. We're not saying for sure if this goes up 5 degrees, the other variable goes down. We're saying it's a likely relationship. So the other way to say that too is if we're looking at y, this y-axis, try to give you something specific. Let's say, let's look at sleepiness and coffee. I was just looking at my coffee list. So if I was to say coffee leads to more tiredness, I could say, if I drink 2 cups of coffee, I notice that I get less alertness before bedtime or something, right? So just hang. I know initially you get alert, but not. But I could also say I'm more tired when I, let's say, wake up in the morning so I need more coffee, right? So it's hard to say whether it's the lack of sleep or the coffee that is directing this relationship. There's just some relationship. Okay, hopefully that made sense. Great. Okay. Yes, we already spoke about this. That's great. So this is just a bit better example. So this would be a correlation of 0 or closer to 0, and this would be closer to a correlation of 1. Luckily, those patterns look like the values that they are. Okay. And again, this is a relationship. We're not saying y affects x or x affects y, that we're just saying that they are related. Okay. Now, our third question that we often want to ask when we're looking at stats is there significance between our two groups or our findings, right? Our correlation or whatever. Is there enough of a difference based off of probability? What is the likelihood that our results are randomly due to chance, or is it highly probable, but that this will occur every time that we go to run this test? That's really what we're looking for when we're looking for significance. Okay, and so what we find here is whether it's a correlational t-test or ANOVA, we're trying to find, is it significant? And what that looks like is, are our findings not due to luck, but what we actually find? And a lot of the times we set this value, a p-value of this. So what we're saying is, based off of this normal curve or this bell curve that we have here on this graph, if we make this cutoff point here at 0.05% of our population or experimental groups, okay, so we have this cutoff threshold. I don't want to ruin the dotted line, kind of here at 0.05. What is the chance? What is the likelihood? What is the probability that if we observe a value here, that it will actually find something there? Like if we ran this 100 times, what is the chance that we'd get a response there, or the most responses end up here? Okay, and so what we're typically finding, or what we're looking for when we're doing this, is we want to find something that is saying, hey, if you set your cutoff threshold here, it is very unlikely to find anything beyond that line. Okay, the probability or likelihood is very, very little getting an observation there. Okay, so what we're saying is it's unlikely to get an extreme result based off of all of your other respondents primarily being here, right? And so this relates to being 5% of your results. So we're saying if we have a statistically significant study that 95% of the time that we run the study, we're likely to get the results we will, or we're likely to observe some sort of a result in this area, okay? So in this part of the bell curve. So we can say predictably, if this is our hypothesis, this is 95% of the time likely to be true, okay? And the fact that maybe 5% of the time, or even less if we observe a smaller point of significance, right? We can set our p-value at 0.05 and actually get a significant value or a level of significance at 0.03, 0.02. That's very significant. 0.01, 0.0001. That's very, very significant, because we're saying it's not just 95%, it's 99.999% significant. We're saying that there's a very, very low chance that what we find is due to randomness, that we're most likely finding a valid result. Okay, and so that's why finding something that's statistically significant is mathematically based off of probability. You are supporting your hypothesis, right? And that's important, right, in science. So again, smaller the p-value, not that we initially set to test at, but what we find, the more significant it is. Okay, let's take a little practice here. Okay, after a review, so we want to see, is there a difference between our groups, and is it significant, right? So is it not just due to chance? Is it highly probable? And again, there's lots of different ways we can look at variability through these tests or correlation. Is there a difference? And what is the relationship is another way of kind of looking at our difference, right? So those two are kind of in the first question. Good. Okay, here's the practice test that I wanted to bring up. So again, pause the video here. Pause, trying to draw your attention back. I know sometimes going through sets and some numbers can be trying, but again, the more specific examples you can come up with, the better for sure. Good. Okay, hopefully everyone's back paying attention. So what I want you to do is go through these questions, pause the video here, and try to interpret two things. So when you're looking at correlation, you're trying to identify the direction of the correlation between, say, the y and x variable for both of these. And then how strong is the relationship, right? Is there some sort of correlation between the two or tying together the two, okay? As far as significance interpretation, based off the p-values, is there significance, and is it like very significant or not significant? Remembering that p-values are set at 0.05 typically, right? Okay, let you pause and work through that. Okay, great. So let's take a little look-see here. And I'll try to describe this a little bit more too, I guess, for you here. So flexibility and performance has a correlation value of 0.98, so that is almost 1, and positive. So if we were to look at this, we'd find a linear tendency, something like that, and then we'd have all our plots pretty darn close to that line on the way up. So that's saying there's a high relationship between as flexibility increases, performance increases. Okay, that's what this study would say. They actually found this isn't necessarily 100% true. You can actually be too flexible and have too much range of motion. That actually increases your chance of getting injured and prolonged injury, but I digress. This is an example. Hydration and injuries. Okay, what happens here? Well, there's a negative 0.22. So we're saying that's 0.2 is 20%. Like that's pretty far from 1, but it's negative. So it looks something like that. And again, there's some maybe relationship, but it's really weak. Maybe we got one over there. And so what are we saying when we're saying that? Well, we're saying that there's a low relationship based off of the 0.22, not the negative sign. I want to make that really clear. And so that means like as my hydration level lowers, gets lower and lower, my chance of injury goes up, right? So this would be like, let's just say this is like 100 up here. Why not? 100% chance of injury, and this is 0. So we can see as hydration goes down, we have our correlation heading this way, which means we get a higher degree of chance of injury. Okay? So that's how we interpret that. If we're looking at our statistical significance, what are we saying here? Well, we're saying PE classes, those that are in PE classes, take PE classes, etc., have a 0.006 improvement or chance of having motor ability. And we're saying that's pretty high, right? If we have 0.05, this is a whole magnitude smaller. It's got a whole one more 0 in there relative to that. So it is very statistical significant. What about employment and happiness? Well, again, if we kind of look at this number, we're getting up to almost like 0.4. And if we're saying, and if we were to make this a percent, that'd be like 40%, whereas this is 5% randomness. Well, I would say that's probably not statistically significant, saying that, if you take that 40% and flip it, we're saying only 60% of what we found is actually valid. So the relationship or cause and effect here between employment and happiness is only supported 60% of the time. Because we're saying again, oh my goodness, that was the worst bell curve ever. Something like this, right? So all of this area here, that's the 40% of our p-value based off of this, which means 60% is here. And recall that this is the stuff that is supported by our hypothesis that employment brings happiness. And yeah, okay, good. Hopefully that helps explain finally what these p-values less than or equal to these numbers mean, and what these R letters equaling a positive or negative lower value than 1, typically, or 1, need. And you can interpret those now. Okay, great. So the last component or last step of what you'll be doing after that is your research literature critique. And this is a large part of where your exam is going to be looking at, and any future reports or evaluations of peer-reviewed literature that you're looking at will be done through this way. So critique as appraisal. I think that's my key point for this, is that you're not just looking at the negative parts of a study when you're looking at critique, okay? You're also looking at positive aspects. So again, looking at not just the poor parts or lacking parts of a study, but the good stuff. Yeah. And part of how we can do this, there's two main ways that I'm going to kind of highlight for you here. Is one, we spoke about it quite a bit, is looking at the validity of what the study is looking at. So is the study actually measuring through its dependent variables what it's intending to measure? Okay. Is it actually measuring the effects of aerobic capacity through a survey? Or would it be better to measure it through doing a VO2 test of some sort, So the latter would be more valid than the former. Okay. Another point that we haven't really spoken about that is related but very much different would be reliability. So when you're talking about reliability, you're talking about the repeatability to get the same results every time you run the test, okay? There's a few different ways this can look, or how this can come up. One, it can be if you have a whole bunch of people or researchers doing a project, what is the reliability between each of those people? And the more subjective the measure is, so the more that my opinion and my bias has on me generating a score for whatever measure, the more likely it is to have poor reliability, right? Because my opinion and thoughts are going to be different than the next person, likely. Okay, this isn't always the case. On the other hand, reliability comes up. Let's say, we'll just focus on that one. That's the main one. Okay, so here's a good example of that, even with actual tools and instruments and stuff. So this is called an FMS, or a functional movement screen test. It has these 7 movements, and an individual will rank it between 0 and 3. Okay, so for each of these, you look at how they perform a certain movement, and you as a practitioner are like 1 or 2, and they have operant definitions for what each category defines based off of what you're seeing. So there's some help there, right? This is called a goniometer, and this has 0 to 360 degrees as far as the increments you can measure. Okay, and you essentially line one of these arms up with, say, like a hip joint and a knee joint, and then you move your leg. Let's say you're moving your leg upward that way at the hip. This is your hip here. And then you see how far you can lift your leg. And then this little line off the tail will give you a change in degrees that you observed from 0, something in there. Okay. Okay. So if you are having 2 individuals have to pick between 0 and 3, and 0 is even just pain, so it's like a straightforward one. So it's really 1 to 3. Or you have individuals try to gauge something between 0 and 360, or even incrementally these little hashtags for each degree. we can think for a moment and go, hey, there's a lot more to choose from on the goniometer than there is on this FMS test. So in between my raters, there's going to be a lot more reliability using this than there is the goniometer. Okay. So again, how reproducible and consistently similar are the results going to be? That's essentially what reliability is looking at. Okay, so it has nothing to do with a valid result as far as statistical significance or anything like that. Okay, good. Yeah, so those are kind of two points that we're looking for. So the fit between the approach and the goal of the study. My approach is trying to assess range of motion. Is it valid to use an FMS or is it valid to use a goniometer? Which one has more validity? I think that's a little bit up for debate. I would potentially argue the goniometer. And then what's more reliable? And I would say, well, if we're looking for inter-rater or between-rater reliability, FMS is probably more reliable as far as its accuracy between measures, between people. Okay, so as an example of both. Good. Next point, aside from looking at how aligned and how well the study actually performed what it intended to, we kind of get to next step as far as applying the study to your particular group. So for example, does the population studied in the study match with yours? And again, there's some flexibility here. And maybe in one study, it looks at a healthy population of adults from 45-year-olds to 80-year-olds, so older, getting to older adulthood. And your client or your population you have is young adults. Well, there are some differences, but depending on what outcome measure you're looking at, it might be okay, right? Measures, are they the same? If you're doing a reaction time test through a visual stimuli and you're looking at a study that has an auditory stimuli, or is that a valid measure in the sense that can you use the same results? Okay, and again, if you do use let's say like different measures and try applying a study, you need to be able to justify that and have some support in doing so. And last but not least, the intervention or experiment protocol. If you're looking at the training effect of a strength program and you are hoping to run a 8-week program and the study only has a 4-week program, can you extrapolate those results? Do you think the results would be the same? A lot of things happen for strength training after 8 weeks. So, is that conducted in a way that's similar enough to what you're doing to be able to use? Okay, so again, that's called generalizability, being able to use, and I would say also applicability, but use your study for your purposes. So if you're a kinesiologist, using it in a clinical setting, or let's say a gym setting, or in your case in the class, are you able to use this to be able to apply to your research experiment? Making sure those align. Okay, great. The last 3 points that you can keep in mind when you're going to critique a paper and or when you're reviewing your papers in preparation for the exam and applying it to your experiments is acronym of RAM. So randomization, assertion, and measures. Okay, or measurements. So when we're looking at it, where was the randomization happening? Okay, typically we want to randomize our groups where possible. Not all methods allow that, and it's not always the best practice in all methodology, but when and where we can, are we randomly allocating our participants to different groups? That adds strength to our study and our research methods. So that's kind of the first one. Second is how did the researchers get their results? So how did the study obtain its participants, but also how did the study obtain its data? Is it through pen and paper? Was it at a point in time when participants were fatigued and not able to answer well? There's a lot of different factors that can come into that. And I would say this is probably one of the better places to be able to critique a research paper. And would we assume any of these ways that they ascertain, let's say, participants affect the results? So, for example, if a lot of research classically has been done at universities, and there's a very specific university student body population. Typically, especially if you're looking at the States, you're looking at a slightly more affluent population. And that inherently has bias. And within that bias of selecting that population, you're excluding a large part of the general population from your study. Just the fact that undergraduate students are becoming more and more educated people, that differentiates them significantly from some of the greater population. And depending on what sort of scores you're looking at, anything to do with health and cognition and stuff like that, obviously this group has a skewed bias in their results. So being able to be aware of those results is important. And then last but not least, again, as it's coming up, measures. What is the measurement tool are you using? Is it actually measuring what you're hoping to measure? And if not, how did that influence the results? Did it minimize it? Did it exaggerate results? I think that's the last step that a lot of students typically miss, is you say, oh, well, there's a small population group. Okay, what effect would that have on the results? They used a Wingate test for measure of anaerobic activity instead of aerobic activity. Okay, fine. What results would we expect? Or how would that have skewed the data that was collected, right? So that kind of next step, logic and explanation, really takes your critique or your appraisal of a peer-reviewed study to the next level. So definitely dive into that and give that some thought and consideration whenever you're doing that. Okay. Great. And that is it. So many of you already at this point have made your groups. You've done some research and are trying to find some peer-reviewed research, and hopefully this will help you analyze it, assess it, and move through it a bit better. And you can start prepping your exam on that study. Okay. Good luck with that. Feel free to email me any questions you have, or try to set up some office hours to be able to have those questions answered. All right. Take care.